Welcome to Sleepy Science Stories. Tonight, we drift through an invisible desert, a vast cosmic void stretching over 2 billion light-years. Scientists call it the KBC void, and it might be the reason our universe appears to expand faster than it should. If we truly live inside this enormous bubble of emptiness, every measurement we make about the cosmos could be distorted. Join me as we explore how this cosmic void reshapes our understanding of space, time, and reality itself. This is, are we living inside a cosmic void? At this very moment, as you listen to these words, you are falling through a hole in space. A hole so vast, so incomprehensibly enormous, that it stretches across 2 billion light-years of cosmic emptiness. Scientists confirmed the existence of this void in the year 2013, and yet most people walking this earth still have absolutely no idea. We live inside something called the KBC void, a cosmic desert of unimaginable proportions, a region where matter itself is 20% thinner, 20% less dense than it should be, according to everything we understand about the universe. This emptiness, this absence of matter, is doing something extraordinary and unsettling. It is warping our measurements of reality itself. The universe, when observed from our position deep within this void, appears to expand faster here than it does anywhere else in the observable cosmos. This apparent acceleration is breaking our most fundamental equations, challenging the very mathematics that we have relied upon to understand the nature of existence. We will journey together through the discovery that shattered our understanding of cosmology, explore the profound question of why 90% of space is hollow and empty, and reveal what it truly means to exist in the cosmic outskirts, in the forgotten corners of the universe. If you are ready to see the universe differently, to perceive reality through a new lens, hit that like button and subscribe to this channel. Prepare yourselves for a journey into the cosmic void. We begin. 3 astronomers were counting galaxies when they noticed something that should have been impossible, something that would challenge decades of cosmological thinking. Ryan Keenan, Amy Barger, and Lennox Cowie, 3 scientists examining the cosmos with patient precision and methodical care, examined 35,000 galaxies in the year 2013. They were mapping the positions of these galaxies across billions of light-years of space, creating a 3-dimensional chart of the cosmos, a detailed map showing where matter concentrates and where it does not. The work was painstaking, requiring them to measure the redshift of each galaxy, the stretching of its light caused by cosmic expansion. From the redshift, they could calculate distance, determining how far away each galaxy sits from Earth. Combined with the galaxy's position on the sky, this gave them full 3-dimensional coordinates. Plot enough galaxies this way and patterns emerge, structures reveal themselves, and the cosmic web becomes visible. The astronomers used data from multiple galaxy surveys, cross-checking their results to ensure accuracy. They employed sophisticated statistical methods to account for observational biases and selection effects. They were looking for the large-scale structure of the universe, the distribution of matter across the biggest scales we can observe. What they found surprised them profoundly. The numbers that emerged from their observations were wrong, not because of any error in measurement or analysis, but because reality itself differed from what theory predicted. Deeply, fundamentally wrong. Everywhere they looked in the regions near Earth, in our cosmic neighborhood, there were fewer galaxies than there should have been. Not slightly fewer, not a small statistical variation that could be explained by random chance. 20% fewer. 1/5 of the expected matter was simply missing. The pattern stretched outward in every direction for 1 billion light-years, forming an enormous sphere of cosmic emptiness with us, with our galaxy, with our solar system, positioned near the center of this vast hollow. This was not a small gap between galaxy clusters, not one of the ordinary voids that pepper the cosmic web. This was a void on a scale that should not exist according to standard cosmology, according to our accepted models of how the universe evolved and structured itself after the Big Bang. The researchers triple-checked their data with methodical care. They used multiple galaxy surveys, cross-referencing observations from different telescopes and different wavelengths of light. They examined the sky from different angles, looking for any possible error in their methodology. The result remained consistent, unwavering, undeniable. Our galaxy, the Milky Way, and everything around it for billions of light years, sits inside an underdense bubble of space, so massive that it dwarfs everything else we have ever observed. The discovery earned a name that sounds almost casual, almost mundane. The KBC Void, using the initials of its 3 discoverers. But there is nothing casual about what this discovery represents, nothing mundane about its implications for our understanding of the cosmos. In the standard model of cosmology, the framework that has guided our thinking for decades, the universe should be roughly uniform when you zoom out far enough. Sure, galaxies cluster together in groups and chains, leaving empty spaces between them. That is expected. That is predicted by our models. Small voids exist throughout the cosmic web, regions where galaxies are sparse. But a region this enormous, this unimaginably vast, with such a significant deficit of matter that pushes the boundaries of what random chance can explain, that challenges the very notion of cosmic uniformity. Computer simulations of how the universe evolved from the Big Bang, sophisticated models that run on the world's most powerful supercomputers, rarely produce voids this large and this empty. The mathematical models predict structures on many scales, yes, voids of various sizes certainly, but something this extreme. When simulations do occasionally produce a void matching the KBC void's characteristics, it requires exceptionally rare initial conditions in the early universe. The statistical probability, calculated by multiple research teams, is less than 1 in 1,000. Some scientists calculated it would take a 10 sigma deviation from average density. 10 sigma means it is so unlikely, so statistically improbable, that you might not find one such void in the entire observable universe. Yet here we are, living inside one, dwelling within it, making our home in this cosmic anomaly. The implications began cascading immediately among the scientific community. If we reside in such an unusual location, such a statistically rare position in the universe, does that bias every measurement we make? When we point our telescopes at distant supernovae, those exploding stars that serve as cosmic mile markers to measure how fast the universe expands, are we seeing the true cosmic expansion rate? Or are we seeing a distorted local version, skewed by our peculiar position inside this massive void? The void hypothesis offered an answer to one of the biggest mysteries in modern cosmology, a puzzle that has troubled scientists for years: the Hubble tension. For years, cosmologists have measured 2 different expansion rates for the universe, depending on whether they look at the ancient universe, the cosmic microwave background radiation from just after the Big Bang, or the nearby universe, using observations of relatively recent supernovae. The numbers disagree by 9%, which sounds small, like a minor discrepancy, but in the precise world of cosmology, this represents a crisis. Both measurements are incredibly precise, refined through decades of careful observation. Both are performed by highly skilled teams using the best instruments humanity has ever built. Both should give the same answer. They do not. If Earth sits inside a massive underdense region, if we are positioned within this cosmic hole, then gravity from the denser matter surrounding the void would pull outward on galaxies within it. That gravitational pull would add extra velocity to their motion away from us, making the local expansion appear faster than the cosmic average. Suddenly, unexpectedly, the conflicting measurements made sense. We are not measuring the universe incorrectly. Our instruments are not flawed. Our mathematics is not wrong. We are measuring the universe correctly, but we are measuring it from inside a hole, from a position that gives us a skewed perspective. This realization changed everything in cosmology, but it also raised an uncomfortable question that cosmologists are still grappling with, still debating in conferences and research papers. If our location in the universe is this unusual, this statistically improbable, can we trust anything we think we know about the cosmos? Can we generalize our observations to make statements about the universe as a whole? What comes next in our journey reveals just how strange our cosmic neighborhood really is, how different the void environment is from the rest of the universe. Cosmic voids are not truly empty, which makes them even stranger, even more fascinating than their name suggests. The word void implies nothingness, complete absence, but that is not quite accurate. Between the lowly scattered galaxies that do exist within voids stretches space that contains mainly dark matter, that mysterious invisible substance that makes up most of the universe's mass. Dark energy, the even more mysterious force driving cosmic acceleration and occasional wisps of hydrogen gas, the simplest and most abundant element in the cosmos. The density of matter in voids is so low that gravity barely functions in the way we normally think about it. Without enough mass concentrated in one place to pull things together, structure formation essentially stops. No new galaxy clusters can form from the sparse material available. No rich superclusters, those massive collections of galaxies, can emerge. The void stays a void, unchanging, expanding, growing emptier with time. This emptiness, this absence of mass, has consequences that ripple through physics itself, affecting the fundamental forces of nature. Gravity is already the weakest of the four fundamental forces in nature by an enormous margin. It requires enormous masses, like planets and stars, to show noticeable effects, to bend space enough that we can observe it. In a void where mass is scarce, where galaxies are separated by hundreds of millions of light years instead of mere millions, gravity becomes even less relevant, even more negligible. The dominant force in voids becomes dark energy, the mysterious pressure, the cosmic repulsion that accelerates the expansion of the universe. In dense regions full of galaxies, regions like the Virgo supercluster or the Shapley supercluster, gravity fights against dark energy in an eternal cosmic tug of war. Gravity works to pull matter together, to slow the expansion. Dark energy pushes outward, working to accelerate it. In those dense regions, gravity is strong enough to slow down the expansion locally, creating bound structures that resist the cosmic flow. Inside voids, gravity loses that tug of war decisively. There simply is not enough mass for gravity to compete effectively. Dark energy wins completely, dominating the dynamics. As a result, voids expand faster than the rest of the universe. They grow like bubbles in foam, pushing their boundaries outward, while the filaments of galaxies around them act as walls, as constraints that define the void's edges. This creates a self-reinforcing cycle, a feedback loop. The more a void expands, the emptier it becomes as the sparse matter within it spreads across ever larger volumes. The emptier it becomes, the weaker gravity becomes within it. The weaker gravity becomes, the more completely dark energy dominates. The more dark energy dominates, the faster the expansion proceeds. And so the cycle continues, the void growing ever larger, ever emptier, ever more dominated by the mysterious force we call dark energy. Scientists confirmed this accelerated expansion through careful observation of void galaxies. They measured how galaxies near void edges move through space compared to galaxies in denser regions. The void galaxies are rushing away from the void center faster than cosmic expansion alone would explain, much faster. Something is pushing them outward, giving them an extra velocity boost. That something is the gravitational pull from all the matter outside the void. This might seem counterintuitive at first. How does gravity from outside the void push galaxies away from the void center? Think of a void as a valley surrounded by mountains in a landscape. Gravity pulls downhill from the mountains toward the valley, following the slope. But since we are talking about space rather than terrain, since we are discussing the fabric of the universe itself, that gravitational pull makes galaxies fall outward from the void center, not inward. They are falling up the gravitational slope toward the denser regions beyond the void boundary. The effect is measurable and significant when you examine the data. Our own galaxy, the Milky Way, the home of billions of stars including our Sun, is moving away from the center of the local void at 600,000 miles per hour. 600,000 miles every hour, driven by this gravitational imbalance, this cosmic push from the universe beyond our empty bubble. The interior of a void becomes a strange place for physics, a laboratory where the normal rules seem different. Light travels through void space, crossing those vast empty regions, experiencing less gravitational influence than light passing through normal space filled with galaxies and dark matter. This affects astronomical observations in subtle but measurable ways. When astronomers study the cosmic microwave background radiation, that faint afterglow of the Big Bang that fills all of space, they notice something peculiar. Light passing through voids appears slightly cooler than light that has travelled through denser regions. The temperature difference is tiny, just a few millionths of a degree, but it is real and detectable with sensitive instruments. The reduced gravity in voids causes less gravitational redshift, less energy loss as light climbs out of gravitational wells. This shows up as cold spots in temperature maps of the early universe. These cold spots, these subtle variations in the cosmic microwave background, line up perfectly with where we observe large voids today. The alignment is not coincidence, it is physics, cause and effect playing out across billions of light years and billions of years of cosmic history. Understanding what makes voids empty, what keeps them devoid of matter, helps explain why they matter so much to our understanding of cosmology. They are not just boring blank spaces between interesting galaxy clusters, mere gaps in the cosmic tapestry. They are laboratories where dark energy dominates completely, where gravity takes a permanent backseat. By studying how matter behaves differently in voids versus dense regions, scientists can test fundamental theories about how the universe works, about the nature of dark energy and dark matter. The KBC void around us might be unsettling because it makes us question our cosmic typicality, our assumption that Earth occupies an average position in the universe. But it also offers a rare opportunity, a unique advantage. We are positioned in exactly the right place to study the universe's most extreme low-density environments. We live within the very phenomenon we are trying to understand. The structure that contains these voids, the framework within which voids exist, is far stranger than anyone imagined when astronomy was young. The universe is not a smooth soup of evenly distributed galaxies, not a uniform fog of matter. Instead, it resembles Swiss cheese, with dense matter forming walls and filaments surrounding enormous hollow pockets. This foam-like architecture is called the cosmic web, and it represents the largest structure in nature, the grandest pattern in existence. Galaxy clusters concentrate at the intersections where multiple filaments meet, creating nodes of intense matter density. These nodes shine brilliantly, with millions of galaxies packed relatively close together, bound by their mutual gravity. Stretching between them run filaments, long chains of galaxy groups that can extend for hundreds of millions of light years across space. These filaments form walls, vast sheets where galaxies concentrate, defining the boundaries of the voids. Between all of this structure lie the voids, enormous regions where galaxies are rare and matter is sparse. The cosmic web looks organic, alive, like a neural network or like the structure of lung tissue. This similarity is not superficial. It arises from the same mathematical principles that govern growth and structure formation in complex systems. Gravity amplifies initial density variations, pulling matter from underdense regions into overdense ones, just as biological growth factors can create branching structures in living tissue. Scientists discovered this foam structure gradually, through decades of galaxy surveys mapping larger and larger volumes of space. In the 1970s, astronomers noticed that galaxies seemed to avoid certain regions. In the 1980s, redshift surveys revealed the first definitive voids, spherical regions millions of light years across containing almost no galaxies. The Boots void, discovered in 1981, was one of the first, spanning 330 million light years and containing only 60 galaxies where thousands would be expected. As surveys expanded, mapping millions of galaxies across billions of light years, the full cosmic web emerged. Cosmologists realized that voids were not rare anomalies, but the dominant feature of the universe's structure. When you map the locations of galaxies in three-dimensional space, the voids leap out immediately. They occupy most of the volume. Roughly 90% of space is void, empty, or nearly empty. Galaxies and galaxy clusters, all the bright shining matter we can see with our telescopes, occupy only 10% of the universe's volume, concentrated in filaments and nodes. This realization was profound. It meant that the universe is mostly empty, that matter is the exception rather than the rule. We live in a universe defined more by what it lacks than by what it contains. The cosmic web structure emerged from tiny quantum fluctuations in the very early universe, in the first moments after the Big Bang. Those fluctuations, variations in density of less than 1 part in 100,000, were amplified by gravity over billions of years. Slightly denser regions attracted more matter, growing denser still. Slightly less dense regions lost matter to their surroundings, becoming emptier. Over time, this process created the dramatic contrast we see today between filaments and voids. Dark matter played a crucial role in this structure formation. Dark matter interacts through gravity, but not through electromagnetic forces, meaning it does not emit or absorb light. This allows dark matter to collapse and concentrate without being slowed by radiation pressure or other electromagnetic effects that affect normal matter. Dark matter formed the scaffolding of the cosmic web first, creating gravitational potential wells into which normal matter, atoms and molecules, could fall and form galaxies. The voids formed passively, as evacuated regions left behind when matter collapsed into filaments. Initially, voids contained some matter, but over time, gravity drained them. Galaxies that formed in void interiors either fell toward the void walls or remained as isolated systems, starved of the gas needed for ongoing star formation. This process continues today. Voids are still growing, still expanding, still becoming emptier. The cosmic web is not a static structure, but an evolving one, driven by the interplay of gravity and dark energy. The KBC void, our cosmic home, fits into this larger picture as one of the largest known voids, but not the only one. Other comparable voids have been detected, each a massive bubble in the foam. The Eridanus supervoid, for instance, stretches across 1 billion light-years and may be responsible for a cold spot in the cosmic microwave background. The Boots void remains one of the most famous, nicknamed the Great Nothing due to its extreme emptiness. These voids come in different types. Some are relatively spherical, like the KBC void. Others are elongated, forming tube-like structures. Some are part of larger complexes, interconnected empty regions forming supervoids. The classification of voids is an active area of research, with scientists working to understand the full variety of void shapes and properties. What all voids share is their effect on the matter within them. Void galaxies tend to be smaller and less massive than galaxies in filaments. They form stars more slowly, having less gas available. Many void galaxies are irregular or dwarf galaxies, lacking the majestic spiral or elliptical shapes common in denser regions. The few large galaxies that do exist in voids, including our own Milky Way if we are truly in a void, are somewhat unusual in their environment. The existence of large galaxies like the Milky Way in the KBC void raises interesting questions. How did such massive galaxies form in an underdense region? The answer likely involves the specific history of our local region, the particular conditions billions of years ago that allowed matter to collect and form our local group of galaxies before the void fully evacuated. Understanding void properties helps cosmologists test their models. If simulations cannot reproduce the observed distribution of void sizes and shapes, something is wrong with our assumptions about initial conditions, dark matter, or dark energy. The cosmic web, including its voids, acts as a test of cosmological theories. Voids also affect other astronomical observations in surprising ways. The motion of galaxies in and around voids creates patterns in the large-scale velocity field. These bulk flows, coherent motions of matter across vast scales, provide information about the mass distribution, including dark matter, that we cannot see directly. Gravitational lensing, the bending of light by gravity, is weaker in voids than in dense regions. This means that void regions of the sky produce less distortion of background galaxies. By mapping where lensing is strong and where it is weak, astronomers can map the distribution of matter, both visible and dark, across the universe. The cosmic microwave background radiation is also affected by voids through two effects. The integrated Sachs-Wolf effect causes photons to gain or lose energy as they pass through evolving gravitational potentials. In voids where gravity is weak and the expansion is accelerating, photons gain slightly less energy falling in than they lose climbing out, resulting in a net cooling. This creates the cold spots we mentioned earlier. The Sunyaev-Zeldovich effect occurs when cosmic microwave background photons scatter off hot gas. In voids where gas is sparse, this effect is weaker, creating another signature of voids in the microwave sky. All of these observational techniques combine to give us a detailed picture of cosmic voids, their properties and their distribution. The picture that emerges is both beautiful and unsettling. Beautiful because of the intricate structure, the cosmic web in all its complexity. Unsettling because it reveals just how empty the universe really is and how unusual our position may be. The question of whether our location in the KBC void affects our understanding of cosmology remains hotly debated. Some scientists argue that the void explains the Hubble tension perfectly. The faster local expansion we measure is not a true cosmic property, but a local effect of our void position. When we observe nearby supernovae, we are seeing objects within or near the void where expansion is genuinely faster. When we measure the cosmic microwave background, we are seeing the entire universe, including regions far beyond the void, giving us the true average expansion rate. The two measurements disagree because they are measuring different things: local void expansion versus global cosmic expansion. This explanation is elegant and solves the problem neatly. If correct, it means there is no crisis in cosmology. The universe is expanding at the rate we measure from the cosmic microwave background. Dark energy behaves as predicted. All our equations work. We were just confused by our unusual location. Other scientists are skeptical. They point out that even accounting for the void, the Hubble tension does not completely disappear in all analyses. Some calculations suggest the void is not quite large enough or empty enough to fully explain the discrepancy. This camp argues that the Hubble tension represents a real problem requiring new physics, perhaps a modification to our understanding of dark energy or gravity itself. The debate continues, with research groups analysing data and running simulations to test both scenarios. Upcoming observations from powerful new telescopes may resolve the question. The James Webb Space Telescope, launched in 2021, can observe distant galaxies and supernovae with unprecedented precision. By mapping the expansion rate at different distances and in different directions, it can test whether the void explanation holds up. If the void explains the Hubble tension, we would expect to see the expansion rate gradually shift as we observe farther from the void center. Galaxies at the void edge should show intermediate velocities between the fast local expansion and the slower global expansion. Galaxies well beyond the void should match the cosmic microwave background prediction. If we observe such a pattern, the void hypothesis wins. If instead, we see that all nearby galaxies show the same fast expansion regardless of direction or distance, even beyond what the void predicts, then something else must be causing the tension. That would point toward new physics, perhaps a varying dark energy or modified gravity. This is why the KBC void is so important. It is not just an interesting feature of our cosmic neighborhood, it is potentially the key to resolving one of the biggest mysteries in modern cosmology. Our position inside this void might be the factor that has been confusing our measurements all along, but there is another possibility, more radical and more troubling. What if the void explains too much? What if our entire understanding of the universe is biased by our void position in ways we have not yet realized? Consider the measurement of dark energy itself. We discovered dark energy by observing distant supernovae and finding that the universe's expansion is accelerating. But if we are in a void, Could that acceleration be at least partially a local effect? Could dark energy be weaker than we think, with the void amplifying what we observe? Some researchers have explored this idea. They found that a void can create the appearance of acceleration even in a universe that is not actually accelerating globally. The void's expansion creates a velocity gradient, with matter moving faster the closer it is to us at the void center. This gradient can mimic the signature of dark energy in supernova data. However, this explanation faces challenges. The cosmic microwave background radiation provides independent evidence for dark energy through its effect on the universe's geometry and evolution. Unless we invoke highly contrived scenarios, dark energy appears real and not just a void artifact. Still, the possibility that our observations are void-biased remains a concern. It speaks to a deeper issue in cosmology, the question of cosmic typicality. Are we typical observers in a typical location, or are we in some way special? The Copernican principle, named after Copernicus, who removed Earth from the center of the solar system, states that we should not assume we are in a special or privileged position. This principle has guided science for centuries. It says that Earth is not the center of the solar system. The solar system is not the center of the galaxy. Our galaxy is not the center of the universe. There is no center. We are typical, ordinary, average. The KBC void challenges this principle. If we live in a void that is a 1 in 1,000 statistical rarity, we are not typical. We are unusual, perhaps highly unusual. This does not mean we are at the center of the universe in any meaningful sense, but it does mean our observations might not represent the cosmic average. Some cosmologists find this acceptable. The universe is large and varied. Someone has to live in the rare voids. We happen to be that someone. Just because our location is unusual does not mean we cannot understand the universe. We just need to account for our position when interpreting data. Others are deeply uncomfortable with the idea. They argue that abandoning cosmic typicality opens the door to all sorts of ad hoc explanations. Any anomaly in our observations could be dismissed as a local effect. We lose the ability to make general statements about the universe because we can always say our location is special. This debate touches on fundamental questions about the scientific method and how we know what we know. Can we trust our observations if we are in an unusual location? How unusual is too unusual? At what point does our position become so atypical that we cannot generalize from it? These questions do not have easy answers. They require careful statistical analysis and philosophical consideration. The key is to use observations from as far away as possible, beyond the void, to check whether our local measurements match the global properties of the universe. Future surveys will help. Projects like the Dark Energy Spectroscopic Instrument, which began observations in 2021, are mapping millions of galaxies across vast cosmic volumes. These maps extend well beyond the KBC void, allowing us to compare void regions with non-void regions. If physics works the same everywhere, we will see consistent patterns. If our void is distorting things significantly, we will see discrepancies. The ultimate goal is to understand the universe as a whole, not just our local neighborhood. Voids are part of that universe, important parts that we need to understand. But we also need to see beyond them to grasp the full picture. As we consider the implications of living in a void, we should also consider what voids mean for structure formation and galaxy evolution. How do voids form, and why do they matter for the bigger cosmic story? The formation of voids is intimately connected to the formation of structure in the universe. After the Big Bang, the universe was almost perfectly smooth and uniform. Almost, but not quite. Tiny quantum fluctuations during inflation, the brief period of exponential expansion in the universe's first fraction of a second, created small variations in density. These variations were incredibly tiny, less than 1 part in 100,000, but they were enough. As the universe expanded and cooled, gravity began to amplify these density variations. Regions that were slightly denser than average attracted more matter from their surroundings. This made them denser still, which increased their gravitational pull, which attracted even more matter. The process fed on itself, creating an exponential growth in density contrast. Meanwhile, the regions that started out slightly less dense lost matter to their denser neighbours. They became emptier, which made their gravity weaker, which made them less able to hold on to the matter they still had. They emptied out further. This is how voids formed. The process was not instantaneous. It took billions of years for the dramatic density contrast we see today to develop. In the early universe, a few 100 million years after the Big Bang, voids were just beginning to form. They were shallow, weakly underdense regions. Galaxies still existed throughout what would become voids, though at slightly lower densities than in denser regions. As time passed, gravity continued its work. Matter flowed out of the proto-voids into the growing filaments. Some of the galaxies that initially formed in void regions fell toward the void walls, joining galaxy groups and clusters there. Others remained isolated, becoming the rare void galaxies we observe today. By the time the universe was a few billion years old, voids had become distinct features. By today, roughly 14 billion years after the Big Bang, voids are mature structures with sharp boundaries and very low interior densities. Dark energy changed the evolution of voids in important ways. In the universe's first several billion years, matter and radiation dominated the cosmic energy budget. Gravity was winning the tug-of-war everywhere, pulling structure together. Voids grew, but only because matter was flowing out of them. They were not expanding faster than the universe as a whole. Around 5 billion years ago, dark energy began to dominate. Its repulsive effect started to accelerate the universe's expansion. In dense regions, gravity still held sway, keeping galaxy clusters bound. But in voids, where gravity was already weak, dark energy took over completely. Voids began to expand faster than the cosmic average. This acceleration of void expansion has consequences. It means that voids are growing not just in physical size, but as a fraction of the universe's total volume. The cosmic web is becoming more void-dominated over time. The filaments and clusters are becoming smaller islands in an ever-expanding sea of emptiness. This trend will continue into the future. As dark energy continues to accelerate the universe's expansion, voids will claim an ever larger share of space. Eventually, billions of years from now, voids will dominate completely. Almost all of space will be void, with the few remaining galaxy clusters separated by distances so vast that they can no longer see each other. The formation of galaxies within voids is a special case of galaxy formation. In dense regions, galaxies form through the hierarchical merging process. Small dwarf galaxies form first. They merge to form larger galaxies. Those larger galaxies merge to form galaxies like the Milky Way. The process continues throughout cosmic history, with major mergers still occurring today. In voids, this process is stunted. There are fewer dwarf galaxies to begin with because the matter density is so low. The distances between galaxies are so large that mergers are rare. Void galaxies tend to evolve in isolation, forming stars slowly from their own gas reservoirs without the fresh gas inflow that comes from mergers and interactions. This affects their properties. Void galaxies are typically smaller, less massive, and have lower rates of star formation than galaxies in filaments. They also tend to have lower metallicity, fewer heavy elements, because heavy elements are produced by stars and dispersed through supernovae. Fewer stars means fewer supernovae, means fewer heavy elements. However, void galaxies are not completely quiescent. They do form stars, just more slowly. They can have bursts of star formation when gas clouds collapse, or when they do occasionally interact with a neighbour. Some void galaxies are actively forming stars today, showing that even in the emptiest regions, the process of creating new suns continues. The Milky Way's presence in the KBC void is somewhat puzzling given these trends. Our galaxy is massive by void standards, with hundreds of billions of stars. It has active star formation, creating several new stars per year. It has a rich satellite system with dozens of small dwarf galaxies orbiting it. All of this suggests our galaxy did not evolve in complete isolation. The explanation likely lies in the local group, the cluster of galaxies including the Milky Way and Andromeda. The local group contains enough galaxies and enough matter that it behaves more like a filament environment than a void environment locally. Gravity keeps the group bound, preventing its members from separating despite the void expansion around them. This is an important point about voids. They are not uniformly empty. Within them can exist bound structures, islands of matter that resist the void expansion. The local group is such an island. On small scales, within the group itself, the environment is not really void-like. It is only when you zoom out to larger scales, looking at the distribution of galaxy groups and clusters across hundreds of millions of light years, that the void nature becomes apparent. This multi-scale structure is characteristic of the cosmic web. Structure exists at many different levels, nested within each other. There are individual galaxies, galaxy groups, galaxy clusters, superclusters, filaments, and voids. Each level has its own dynamics. Understanding voids requires understanding how these scales interact. The motion of the local group relative to the cosmic microwave background provides another clue about our void environment. The local group is moving at about 600 kilometers per second, or roughly 600,000 miles per hour, relative to the rest frame defined by the microwave background. This motion is driven by gravitational attraction toward the matter concentrations outside the void, particularly the Shapley supercluster, a massive collection of galaxies about 650 million light-years away. This bulk motion shows that even though we are in a void, we are not isolated from the rest of the universe gravitationally. The mass outside the void pulls on us, driving our motion through space. Over billions of years, this motion will eventually carry the local group toward denser regions, though dark energy may prevent us from ever actually reaching them. The study of voids has practical applications beyond pure cosmology. Voids serve as laboratories for testing dark matter and dark energy theories. Because voids are so dominated by dark energy, they are sensitive to its properties. If dark energy varies in strength over time or space, voids would show the effects clearly. Similarly, modified gravity theories, alternatives to dark energy that attempt to explain cosmic acceleration through changes to Einstein's equations, make specific predictions about void properties. By measuring void shapes, expansion rates, and galaxy distributions, scientists can test these theories. Voids also provide a clean environment for studying galaxy evolution. In dense regions, galaxies constantly interact with each other and with the hot gas-filling galaxy clusters. These environmental effects complicate the study of how galaxies form and evolve. In voids, galaxies are isolated, evolving largely on their own. This makes them simpler to understand, allowing cleaner tests of galaxy formation theories. The cosmic web as a whole, including voids, is a fossil record of the early universe. The patterns we see today in the distribution of galaxies and voids originated from quantum fluctuations during inflation. By studying the cosmic web's structure, we are probing conditions when the universe was less than a trillionth of a trillionth of a trillionth of a second old. The fact that we can do this, that quantum events in the universe's first instant left imprints we can measure today, is extraordinary. The next major surveys in astronomy will map the cosmic web in unprecedented detail. Projects like the Vera Rubin Observatory, which will begin full operations in the mid-2020s, will photograph the entire visible sky repeatedly. Over 10 years, it will detect billions of galaxies, creating a three-dimensional map of cosmic structure far more detailed than anything before. This map will include tens of thousands of voids at all distant scales. By comparing the properties of voids at different distances, astronomers can study how voids evolve over cosmic time. Voids in the distant universe, seen as they were billions of years ago, should be shallower and less developed than nearby voids. Observing this evolution tests our models of structure formation. The map will also reveal whether the KBC void is truly unusual, or if voids of this size are more common than current surveys suggest. If many similar voids exist, our location becomes less special. If the KBC void is one of the very largest or emptiest, the question of why we find ourselves here becomes more acute. Beyond the next decade, even more ambitious projects are being planned. Space-based surveys with telescopes operating beyond Earth's atmosphere will map the universe in infrared light, penetrating dust and revealing galaxies too faint for ground-based telescopes. These surveys will extend to greater distances, potentially mapping the universe when it was less than 1 billion years old. At those early times, voids were just beginning to form. Observing proto-voids, the seeds of today's enormous empty regions, will test whether our understanding of structure formation is correct. If the models predict proto-voids where we observe them, that validates our theories. If the observations disagree with predictions, we will need to revise our understanding. The study of cosmic voids is entering a golden age. The data pouring in from surveys and the computational power to analyze that data are both growing exponentially. In the next decade or two, we will likely answer many of the open questions about voids and about our position in the KBC void. But some questions may remain unanswered for longer. The ultimate fate of voids, the long-term evolution of cosmic structure, depends on the nature of dark energy. And dark energy remains deeply mysterious despite decades of study. What is dark energy? This question haunts cosmology. We know dark energy exists because we observe its effects. The universe's expansion is accelerating, and dark energy is the name we give to whatever causes that acceleration. But we do not know what dark energy is made of, why it has the strength it does, or whether it will remain constant forever. The simplest explanation for dark energy is that it is a cosmological constant, an energy inherent to space itself. In this view, every cubic meter of space contains a small amount of vacuum energy. As the universe expands and creates more space, the total amount of dark energy increases. This makes the expansion accelerate faster and faster over time. The cosmological constant has a curious history. Einstein introduced it in 1917 to make his equations allow for a static universe. When the universe's expansion was discovered in the 1920s, Einstein abandoned the cosmological constant, reportedly calling it his biggest blunder. For decades, it was forgotten or set to zero in calculations. Then, in the late 1990s, observations of distant supernovae revealed cosmic acceleration. The cosmological constant was back, only now it was called dark energy. If dark energy is a cosmological constant, its strength should never change. It is simply a property of space, fixed and eternal. In that case, the future we described earlier holds. Voids will expand forever, galaxy clusters will become isolated islands, and eventually the universe will become cold, dark, and empty. But dark energy might not be a cosmological constant. It could be a dynamic field, something that changes over time. Various theories propose different candidates for what this field might be, with names like quintessence or phantom energy. These theories make different predictions about dark energy's evolution. Some models have dark energy weakening over time. In those scenarios, the universe's acceleration would slow, possibly stopping altogether. Voids would stop expanding faster than the cosmic average. The cosmic web structure would freeze into its current configuration rather than continuing to evolve. Other models have dark energy strengthening. In the most extreme versions, dark energy could strengthen so much that it eventually rips apart bound structures. First, galaxy clusters would be torn apart, then galaxies, then solar systems, then planets, then atoms themselves. This scenario is called the Big Rip, and it would end the universe in a cataclysmic disintegration. Fortunately, current observations suggest this is unlikely. Distinguishing between these possibilities requires measuring dark energy's properties with great precision. Voids are one of the tools for doing this. Because dark energy dominates in voids, its properties are more visible there. By studying how voids expand and evolve, cosmologists can constrain what dark energy is and how it behaves. Current observations favor the cosmological constant explanation. Dark energy appears to be constant in time and uniform in space, but the measurements are not yet precise enough to rule out small variations. Future surveys will improve the precision, potentially revealing whether dark energy is truly constant or slowly evolving. The nature of dark energy is connected to fundamental questions in physics. Why does the vacuum have the energy density it does? Quantum field theory, the theory describing subatomic particles and forces, predicts a vacuum energy density many orders of magnitude larger than what we observe. The discrepancy is 120 orders of magnitude, making it arguably the worst prediction in the history of physics. This problem, called the cosmological constant problem, suggests that our understanding of quantum mechanics or gravity or both is incomplete. Solving it might require a theory of quantum gravity, a framework that unifies quantum mechanics with Einstein's general relativity. Such a theory has been the holy grail of physics for decades, pursued through approaches like string theory or loop quantum gravity. Voids and the cosmic web might provide clues toward that theory. They are probes of gravity and dark energy on the largest scales, scales where quantum effects are usually negligible. But if quantum mechanics and gravity are unified in some deep way, large-scale structure might contain signatures of that unification. This brings us to another deep question about voids and cosmic structure. Is the universe infinite? Does space go on forever in all directions, or is it finite with some kind of boundary or wraparound topology? General relativity allows for both possibilities. The universe could be infinite, extending to arbitrarily large distances. Or it could be finite but unbounded, like the surface of a sphere, where you can travel in any direction indefinitely without reaching an edge, but the total volume is still finite. Current observations suggest the universe is either infinite or so large that its curvature is undetectable. The cosmic microwave background radiation shows a nearly flat geometry consistent with infinite extent. But the measurements are not perfect. A very large finite universe would be indistinguishable from an infinite one. If the universe is infinite, there are infinite voids, infinite galaxies, infinite stars. Everything that can happen within the laws of physics happens infinitely many times. There are infinite copies of Earth, infinite versions of you reading these words. This leads to strange philosophical implications about identity and uniqueness. If the universe is finite, even if inconceivably large, there is a limit to how much structure exists. There are only a finite number of voids, galaxies, and planets. The universe is unique, and everything in it is unique. This seems more intuitive, but raises questions about what lies beyond the boundary, beyond which we will never receive information. Voids within our observable universe are at least measurable and understandable. Voids beyond the cosmic horizon are forever beyond our reach. If the universe is infinite, most of it is and always will be invisible to us. We see only a finite sphere, our observable universe, within the infinite whole. This limitation is humbling. It means that no matter how powerful our telescopes become, no matter how much we learn, there will always be more that we cannot know. The universe's full extent, its global properties, and whether our local observations truly represent cosmic averages may remain mysteries. Some cosmologists find this uncomfortable. It violates the principle that science should be able to answer any question given enough time and data. Others embrace it as a fundamental feature of cosmology. We are embedded in the universe we study. We cannot step outside to view it objectively. Our observations are necessarily limited by our location and by the finite speed of light. Voids remind us of this limitation. The KBC void affects our observations, potentially biasing them. We try to account for this bias, to see beyond our local environment, but we can never be certain we have succeeded completely. There may be features of the universe far beyond the KBC void that we have not encountered, structures or phenomena that would change our understanding if we knew about them. This possibility keeps cosmologists honest. It reminds us that our theories are based on limited data from a limited volume of space. Extrapolating to the entire universe requires assumptions that we can test but never prove absolutely. Despite these limitations, we have learned an enormous amount about the universe. From our position inside a void, we have mapped the cosmic web across billions of light years. We have measured the universe's age, composition, and expansion history. We have traced structure back to the Big Bang and forward to the distant future. This is an impressive achievement given our constraints. The study of voids has contributed significantly to this knowledge. Voids are not just empty space to be ignored. They are informative, revealing how gravity and dark energy shape the universe. They challenge our assumptions and force us to question whether our observations are typical. They provide laboratories for testing fundamental physics in extreme conditions. As we continue exploring voids, we will learn more about dark energy, dark matter, and gravity. We will refine our measurements of cosmic expansion and structure growth. We will better understand our place in the cosmic web and whether living in the KBC void truly makes us unusual. But beyond the scientific details, voids teach us something profound about the nature of existence. They reveal that emptiness is fundamental to the universe's structure. The cosmos is not a crowded place filled with matter. It is a vast expanse of near-nothingness, punctuated by rare concentrations of stars and galaxies. Most of space has never been touched by matter, never been lit by a star, never been affected by anything except the relentless expansion driven by dark energy. This emptiness is not dead or sterile. It is dynamic, expanding, evolving. It shapes the behavior of matter through its presence, or rather through its absence. Voids are as much a part of the universe's story as galaxies are. Understanding voids is understanding the cosmos. As our journey through cosmic voids continues, we must now consider their deep past and distant future. What is the ultimate fate of voids? Where does this story end? The future evolution of voids depends critically on the nature of dark energy. If dark energy remains constant, a cosmological constant, then the universe's fate is determined. The expansion will continue to accelerate forever. Voids will grow larger and emptier. The cosmic web will stretch until its filaments break apart into isolated galaxy clusters. On timescales of hundreds of billions of years, galaxy clusters themselves will begin to evaporate. Galaxies within them will undergo close encounters, with some galaxies being flung out of the cluster at high speeds, while others spiral inward and merge. Eventually, each cluster will be reduced to a single supermassive galaxy surrounded by a halo of orphan stars and the occasional dwarf galaxy. These island galaxies will drift farther and farther apart as the universe expands. After several 100 billion years, galaxies that are not gravitationally bound to each other will be separated by such vast distances that their light can no longer reach each other. The cosmic horizon, the boundary of the observable universe, will contract from each galaxy's perspective. Eventually, an observer in one of these galaxies would see only their own galaxy in an otherwise empty sky. The cosmic microwave background would have redshifted to such long wavelengths that it would be undetectable. All evidence of the Big Bang, of cosmic expansion, of the existence of other galaxies would be gone. Imagine a civilization arising in such a galaxy billions of years from now. What would they be able to learn about the universe? Their sky would be nearly empty except for the stars of their own galaxy. There would be no evidence of the cosmic microwave background because it would be too faint to detect after extreme redshifting. There would be no distant galaxies to measure cosmic expansion, no supernovae to trace acceleration. They would be cosmologically isolated, unable to observe the larger universe because light from beyond their immediate vicinity could not reach them anymore. Such civilizations might conclude they live in a static island universe surrounded by infinite empty space, never suspecting the vaster cosmos beyond their horizon. They would have no way to discover the Big Bang, no evidence that the universe had a beginning or that space is expanding. their cosmology would be fundamentally incomplete through no fault of their own, simply because they exist too late in cosmic history. This scenario, sometimes called the dark future or the cosmological dark age, is the inevitable consequence of accelerating expansion. It represents a fundamental limitation on what can be known about the universe. Future civilizations will have access to less information than we do today. They will be unable to make discoveries that we take for granted. Even within our own void, the long-term future looks increasingly lonely. The Milky Way and Andromeda galaxies will merge in approximately 4 billion years, forming a giant elliptical galaxy. This merged galaxy is sometimes called Milkomeda or Milkdromeda in popular science literature, though the actual name that future civilizations might give it is unknown. This merged galaxy will be the dominant structure in our local group of galaxies. But the local group itself will become increasingly isolated from the rest of the universe. Other nearby galaxy groups, like the Leo spur, the small collection of galaxies in the direction of the constellation, Leo, or the massive Virgo cluster, the nearest large cluster of galaxies, will recede beyond our cosmic horizon within tens of billions of years. The merged Milkomeda galaxy will find itself essentially alone in an expanding void. Star formation within this galaxy will gradually cease as gas is consumed or expelled. The galaxy will fade, containing only old red stars and eventually just white dwarfs, neutron stars, and black holes. The night sky will darken as fewer and fewer stars remain active. Planets still orbiting these dying stars will experience colder and colder conditions as stellar output declines. On even longer timescales, measured in trillions of years rather than billions, stars will become increasingly rare as their nuclear fuel is exhausted. Galaxies will consist mainly of dead stellar remnants that are slowly evaporating into space through gravitational interactions. When stars pass close to each other, the gravitational interaction can change their orbits. Sometimes this gives a star enough velocity to escape the galaxy entirely, flying off into intergalactic space. Over trillions of years, galaxies gradually dissipate through this process. Black holes will dominate the remaining mass in galaxies. Stellar mass black holes formed from massive star deaths. Supermassive black holes are galaxy centers growing through accretion and mergers. These black holes will slowly grow by accreting whatever material remains available. But accretion will become increasingly rare as galaxies empty out. Black holes will spend most of their time doing nothing, simply existing in the darkness. Eventually, after incomprehensibly long timescales, even black holes will evaporate through Hawking radiation. This is a quantum mechanical process predicted by physicist Stephen Hawking in the 1970s. Quantum effects near a black hole's event horizon allow particle-antiparticle pairs to form, with one particle falling into the black hole while the other escapes. This slow leak of particles carries away the black hole's mass. The process is incredibly slow. A solar mass black hole takes 10 to the 67 years to evaporate. A supermassive black hole of 1 billion solar masses takes 10 to the 100 years. These timescales are so long that the usual language of time becomes meaningless. The current age of the universe is only 10 to the 10 years, 14 billion years. The timescale for black hole evaporation is trillions of trillions of trillions of times longer. It is closer to eternal than to any timescale we can intuitively grasp. After the black holes evaporate, the final state of the universe will be a diffuse sea of elementary particles and radiation expanding forever into darkness. The temperature will approach absolute zero. Entropy will be maximized. Nothing will happen because there will be insufficient energy concentration anywhere to drive any process. This is sometimes called the heat death of the universe, an unfortunate name because the universe will be cold, not hot. It represents the ultimate equilibrium state where no further change is possible. Voids will have consumed everything by this point. The distinction between void and non-void will be meaningless because everything is void. The last remnants of cosmic structure will have dissipated into the void's infinite expanse. The cosmic web we observe today, with its intricate filaments and clusters, is a temporary phase in cosmic evolution, a brief moment of structure formation between the smooth early universe and the smooth final state. This bleak future is many billions of years away and depends on dark energy continuing to accelerate expansion as a cosmological constant. If dark energy changes in strength or even in sign, the future could be dramatically different. If dark energy weakens over time, cosmic acceleration might slow or stop. In that case, the universe might coast at constant expansion velocity, or even begin to contract. A contracting universe would bring galaxies back together, voids would shrink, the cosmic web would collapse. Eventually, all matter would merge into a cosmic fireball, a big crunch that mirrors the Big Bang in reverse. Whether the universe would rebound from a big crunch, creating a new expansion phase in a cyclic model, is unknown. Some theories allow for such bounces. Others predict that the crunch is the end, a singularity where the laws of physics break down. If dark energy strengthens over time, the future is even more dramatic. Strong enough dark energy can overcome not just the expansion, but even the gravity holding bound structures together. First, galaxy clusters would be torn apart as dark energy pulls their member galaxies away from each other. Then galaxies themselves would disintegrate as stars are pulled from their orbits. Solar systems would be disrupted, with planets torn from their suns. Eventually, even atoms would be ripped apart as dark energy overwhelms the electromagnetic forces holding electrons to nuclei. This catastrophic end is called the Big Rip. The Big Rip would occur on finite timescales if dark energy strengthens sufficiently. Calculations suggest it would happen within tens of billions of years in models where dark energy increases as rapidly as observations currently allow. The universe would end not with a whimper, but with a violent destruction of all structure. Current observations suggest dark energy is constant or nearly constant, making the Big Rip unlikely. But the uncertainty in measurements leaves room for slow evolution. Only continued observation over many years can narrow down dark energy's properties precisely enough to rule out dramatic future scenarios. Regardless of which future comes to pass, voids play a central role. They are the stage on which the universe's final act will unfold. Understanding voids is understanding the cosmic endgame. But while we contemplate these distant futures, there is one more immediate question about our place in the void. If we live inside a cosmic void, are there other civilizations experiencing the same situation? This question connects the study of voids to the broader search for life in the universe. The distribution of matter throughout the cosmos affects where life can emerge and evolve. Galaxies need sufficient heavy elements to form rocky planets like Earth. Those heavy elements are created by stars through nuclear fusion and scattered through space by supernovae. The first generation of stars contained only hydrogen and helium from the Big Bang. They could not form rocky planets. Only after those stars died and enriched space with heavier elements could later generations of stars form planets suitable for life. This means that life requires a certain level of chemical enrichment, a certain metallicity in astronomical terms. Metallicity refers to the abundance of elements heavier than hydrogen and helium. In dense regions like galaxy clusters, metallicity tends to be higher because more generations of stars have lived and died, producing more heavy elements. In voids, metallicity is lower because fewer stars have formed. This might suggest that voids are poor environments for life. However, there are counter-arguments. Dense regions like galaxy clusters can be violent environments. Galaxies in clusters frequently collide and merge. Active galactic nuclei, supermassive black holes at galaxy centers, pump enormous amounts of energy into their surroundings, potentially disrupting planet formation or sterilizing existing planets with radiation. Supernova rates are higher in regions of active star formation. Gamma-ray bursts, catastrophically energetic explosions associated with certain supernovae, could sterilize planets within thousands of light years of their origin. Voids, in contrast, offer a quieter environment where galaxies evolve more peacefully. Stars form at a moderate pace. Planets have billions of years to develop complex ecosystems without catastrophic interruptions. Major collisions and mergers are rare. Active galactic nuclei are less common. This stability might make void galaxies ideal nurseries for complex life, despite the lower metallicity. The lower metallicity in voids could be offset by the longer timescales available for chemical enrichment to occur naturally through stellar evolution. Even if heavy elements are produced more slowly, given enough time, sufficient quantities can accumulate. Life might take longer to arise in void galaxies, but once it does, it might have billions of years to evolve undisturbed. Arguments against void favorability for life focus on resources and opportunities. Void galaxies tend to be smaller and less massive than galaxies in filaments. They form fewer stars overall, meaning fewer planetary systems and fewer opportunities for life to arise. The lower metallicity means that even when planets do form, the first generations are more likely to be gas giants rather than rocky worlds. Life as we understand it requires complex chemistry involving carbon, oxygen, nitrogen, and other heavy elements. These elements are simply scarcer in void environments. Additionally, the isolation of void galaxies might limit the spread of life if panspermia plays a role. Panspermia is the hypothesis that life can transfer between planetary systems via meteorites or other material ejected during impacts. In dense regions, where stars are relatively close together, material ejected from one planetary system might seed life in another nearby system. In voids, the vast distances between stars and galaxies make such transfers nearly impossible. Each void galaxy would have to develop life independently without any possibility of receiving seeds from elsewhere. The question of whether voids favour or disfavour life remains open. We have a sample size of one, Earth, which exists in what may be a void galaxy, but we cannot draw strong conclusions from a single example. The discovery of life elsewhere, whether in our galaxy or in other galaxies, would help answer this question. If we find life is common in void galaxies despite the lower metallicity, it would suggest that stability matters more than abundance. If we find life is concentrated in denser regions, it would confirm that resource availability is critical. If other civilizations do exist in voids, would they develop the same understanding of cosmology that we have? This is a fascinating question with profound implications. The answer depends on how isolated they are and what observable phenomena are available to them. A civilization in a dense cluster, like the Virgo cluster, would observe a rich, crowded sky. Nearby galaxies would be visible even to their naked eye. Early in their scientific development, they would discover that the universe contains many galaxies and that those galaxies are moving away from each other. Measuring cosmic expansion would be straightforward because they could observe a large sample of galaxies at various distances. For such a civilization, the Big Bang model would be natural and quickly accepted. The cosmic microwave background would be easily detected. Dark energy and dark matter would be discovered through their gravitational effects on nearby structures, but a civilization deep inside a void might struggle. With only a few nearby galaxies to observe, measuring cosmic expansion becomes challenging. They might initially think their galaxy is the entire universe, with the other visible galaxies being minor companions. Without sufficient data on galactic distances and velocities, they might not discover Hubble's law, the relationship between distance and recession velocity that reveals cosmic expansion. The void's effect on local measurements could further confuse them. If they do eventually measure the expansion rate using nearby galaxies within their void, they might calculate a value affected by the void's peculiar dynamics. When they later discover the cosmic microwave background and measure a different expansion rate from it, they would face a tension similar to our Hubble tension, but they might lack the context to interpret it correctly. They might develop alternative models to explain their observations without invoking cosmic expansion or dark energy. Perhaps they would imagine a static universe with some other mechanism causing galactic redshifts. Such models would be wrong, but they might fit the limited data available to avoid civilization. This thought experiment raises the meta-question of whether our own cosmology is affected by our void location in ways we have not yet realized. We think we understand the universe fairly well based on observations from within the KBC void. We have measured cosmic expansion, detected the cosmic microwave background, discovered dark matter and dark energy, and traced structure back to the Big Bang. But what if there are systematic biases we have not accounted for? What if the universe beyond our void looks fundamentally different from what we observe locally? Future observations extending well beyond the void should test this possibility. If distant regions of the universe confirm our local conclusions, if we see the same cosmic expansion rate, the same dark energy effects, and the same structure formation patterns, then we can feel confident our understanding is correct despite our void location. If distant regions reveal systematic differences, unexpected patterns that our current theories cannot explain, we may need to revise our entire cosmological framework. This is the ultimate test of whether void dwellers like us can accurately understand the cosmos, or whether we are forever limited by our unusual vantage point. The question remains open, awaiting better data from deeper surveys and more powerful telescopes. The search for life in the universe has traditionally focused on specific factors like the habitable zone around stars, the liquid water temperature range where life as we know it could exist. Scientists look for biosignatures in exoplanet atmospheres, chemical indicators like oxygen or methane that might be produced by living organisms. They search for technosignatures, signs of advanced civilizations such as radio transmissions, laser pulses, or megastructures that alter starlight in detectable ways. Perhaps the search should also consider the large-scale cosmic environment, the position within the cosmic web. Civilizations in voids might be more common if voids provide stable conditions favorable for the long-term evolution of complex life. Or they might be rare if voids lack sufficient chemical resources and stellar populations to produce many habitable planets. Either way, the cosmic web structure influences where we should direct our attention and what kinds of environments might harbour life. If we are typical representatives of void civilizations, a big if given our sample size of one, then other intelligent species might also be wondering whether their cosmological measurements are distorted by their location in cosmic structure. They might also be looking for signals from beyond their local void, hoping to contact civilizations in different environments with different perspectives on the universe. The diversity of cosmic environments might mean that civilizations experience very different observable universes depending on where they happen to live. Communication between civilizations in different parts of the cosmic web could be valuable for exactly this reason. Comparing observations from different locations would reveal biases and systematic errors that are invisible to any single civilization. A civilization in a dense cluster could tell us what the universe looks like from their perspective. A civilization in a different void could compare their measurements with ours. Together, these multiple perspectives would build a more complete and accurate picture of cosmic reality. Of course, communication across such vast distances faces enormous challenges. Radio signals travelling at the speed of light take millions of years to cross the distances between galaxies in our local region, much less to reach other voids hundreds of millions or billions of light years away. Any conversation would require patience measured in geological or evolutionary timescales. By the time a response arrives, the civilization that sent the original message might no longer exist, having gone extinct or evolved beyond recognition. Despite these challenges, the possibility of communication is not zero. A sufficiently advanced and long-lived civilization might attempt it. They might send messages to many target galaxies, hoping that at least some host civilizations capable of receiving and responding. Over millions of years, a slow trickle of information could flow between distant parts of the universe, building a cosmic network of knowledge. Such a network might already exist without our knowledge. If civilizations millions or billions of years older than humanity are communicating across cosmic distances, their transmissions might pass through our region of space unnoticed. We might not recognize them as artificial signals. Or we might not be looking at the right wavelengths, in the right directions, or with sufficient sensitivity. The search for extraterrestrial intelligence, SETI, has expanded in recent decades to consider a wider range of possible signals and technosignatures, but it remains limited by the assumptions we make about what civilizations might do and how they might communicate. A truly alien intelligence might use methods we have not imagined. The vastness of voids and the isolation they impose might actually favor certain communication strategies. If civilizations are rare and scattered across vast distances, they might build powerful beacons designed to be visible across billions of light years. Such beacons might use high-energy phenomena, perhaps engineered to modulate the light from entire stars or even from supermassive black holes at galaxy centers. The energy requirements would be enormous, but an advanced civilization harnessing the power of their entire galaxy could conceivably create such beacons. Alternatively, civilizations might focus on preserving knowledge for future discovery rather than real-time communication. They might encode information in durable physical artifacts and send them on trajectories that will pass through many star systems over millions of years. Any civilization discovering such an artifact would gain access to the knowledge it contains. This approach, sometimes called a time capsule or library strategy, does not require simultaneous existence of sender and receiver. These speculations bring us back to the fundamental strangeness of living in a void. Our cosmic environment shapes not just our observations of the universe, but potentially our opportunities for contact with other minds. The KBC void is not just a scientific curiosity. It is the context for our entire existence, affecting everything from the accuracy of our cosmological measurements to the likelihood that we will ever encounter other intelligent species. We find ourselves living inside a cosmic hole 2 billion light years wide. This is not metaphor or speculation or science fiction. This is observational fact. The KBC void is real and measurable. Its effects on light, on gravity, on the motion of galaxies are all detectable with our telescopes and instruments. Whether the void explains the Hubble tension completely or only partially remains debated. Whether it requires modified theories of gravity or can be accommodated within standard cosmology is still uncertain. Whether it makes our position in the universe unusually atypical or merely somewhat unusual depends on how you interpret the statistics and how common such voids truly are. These questions remain open, subject to ongoing research and future observations. But one thing is absolutely certain, beyond any doubt. The universe is far stranger, far more interesting, far more complex than we imagined just decades ago when cosmology was a fledgling science. Our place within this universe is more unusual than we ever suspected when we assumed Earth occupied a typical, average, unremarkable position in a uniform cosmos. We are cosmic castaways in a very real sense, drifting through a desert of space that is emptier than most of the universe, measuring a cosmos that may not appear quite the same from our location as it would from elsewhere. We live on an island of matter in an ocean of void, looking outward at a universe shaped by forces we are only beginning to understand. The voids that dominate cosmic structure are not merely empty background, not just the spaces between interesting objects. They are dynamic, evolving, active components of the universe's story. They shape how matter moves, how light travels, how structure forms and dissolves over billions of years. They may determine the ultimate fate of everything that exists. As we continue our exploration of the cosmos in the coming decades and centuries, as we build more powerful telescopes and conduct deeper surveys, as we map ever larger volumes of space with ever greater precision, we will learn more about voids and about our particular void. We will refine our measurements of cosmic expansion and determine whether our location truly biases them. We will discover whether the KBC void is exceptional or merely one of many similar structures scattered through the observable universe. We will, perhaps, even learn whether other civilizations exist within voids like ours, whether they have struggled with the same questions about their cosmological measurements, whether they have also wondered if their position in the universe is typical or strange. The answers to these questions will shape our understanding not just of physics and astronomy, but of our place in the vast tapestry of existence. For now, we live with uncertainty, with open questions, with the knowledge that we dwell inside a cosmic anomaly whose full implications we are still working to understand. We fall through this hole in space, this 2 billion light-year wide desert of near emptiness, carrying with us our questions and our instruments and our relentless curiosity about the nature of reality. The journey continues. The void surrounds us. And somewhere out there, beyond the edges of our cosmic bubble, lies the rest of the universe, waiting to be discovered, waiting to reveal whether what we see from here truly represents the cosmos as a whole, or merely one peculiar perspective among many. We are void dwellers, makers of observations, seekers of truth in a strange corner of a vast and mysterious universe, and this perhaps is the most profound realization the void can offer. That strangeness is not an exception, but a rule, that the cosmos is endlessly varied and surprising, and that our position within it, unusual though it may be, gives us a unique window into the fundamental nature of everything that exists. The implications of void physics extend far beyond abstract cosmology into questions that touch on the very foundations of how we understand reality. When we consider that we are measuring the universe from within a statistical anomaly, we must ask ourselves how many other anomalies might exist that we have not yet recognized. How many of our observations, carefully made with precision instruments and analyzed with sophisticated mathematics, might be subtly influenced by factors we have not considered. This epistemological humility, this recognition that our knowledge is always provisional and subject to revision, is essential to good science. It keeps us honest, prevents us from becoming too confident in our theories, and drives us to seek better data and better understanding. The void forces us to confront these questions directly. It challenges us to prove that our observations from this unusual location can still yield universal truths about the cosmos. The mathematical framework we use to describe voids comes from Einstein's general theory of relativity, the geometric theory of gravity that has been tested extensively and passed every test with remarkable accuracy. In general relativity, matter and energy curve space-time, and objects move along the curved paths that result. This simple principle explains everything from planetary orbits to black holes to the expansion of the universe itself. In a void, where matter is sparse, space-time is less curved than in denser regions. The geometry approaches flatness, the special case where space-time has no curvature at all. This flat geometry has consequences for how light travels and how objects move. Light rays follow straighter paths through voids than through matter-rich regions. Gravitational lensing, the bending of light by gravity, is weaker. Time dilation effects are smaller. These differences might seem subtle, but they accumulate over the vast distances involved in cosmology. Light travelling billions of years through voids experiences different effects than light travelling through filaments in clusters. When we observe distant galaxies and supernovae, we must account for the path their light took through varying density regions to reach us. The void affects the light's journey in ways that can mimic or mask other cosmological effects. Separating these effects requires detailed modelling. Cosmologists build computer simulations that track how light propagates through realistic distributions of matter, including voids. They compare the predictions from these simulations to actual observations, adjusting their models until they match. This process, called forward modelling, allows them to account for void effects and extract the underlying cosmological parameters we care about, like the Hubble constant and the dark energy density. The precision required for this work is extraordinary. Cosmological parameters need to be measured to better than 1% accuracy to distinguish between different theoretical models. A void that introduces even a small systematic bias can throw off these measurements significantly. This is why understanding the KBC void and its effects is so critical to modern cosmology. Recent studies have attempted to quantify exactly how much the void affects measurements, like the Hubble constant. The results are still debated, with different research groups using different methodologies and reaching different conclusions. Some find that the void can account for most or all of the Hubble tension, while others find it explains only a fraction of the discrepancy. The range of results reflects the difficulty of the problem and the uncertainties involved in modelling complex cosmic structures. One approach to testing the void hypothesis is to measure the expansion rate in different directions on the sky. If the void is responsible for the Hubble tension, we should see directional variations. The expansion should appear faster in directions looking through the void centre and slower in directions toward the void walls or beyond. Several teams have searched for such directional dependence. The results are intriguing but not yet definitive. Some studies find hints of the expected pattern, while others see no significant directional variation. More data is needed to reach a firm conclusion. Another approach is to measure the void's density profile directly by counting galaxies at different distances from its centre. The KBC void studies have done this, establishing that the underdensity extends for roughly 1 billion light-years in all directions from the Milky Way's position. But the exact shape of the density profile, how quickly the density rises as you move from the void centre toward its edges, remains uncertain. Better measurements of this profile will improve predictions for how the void affects cosmic expansion measurements. The void also affects measurements of dark matter through its gravitational influence on matter distribution. Dark matter, the invisible substance that makes up 85% of the universe's matter, reveals itself only through gravity. We map dark matter by observing its gravitational effects on visible matter and on light. In voids, where both dark matter and visible matter are sparse, these effects are subtle and hard to measure. Yet understanding dark matter distribution in voids is essential for testing dark matter theories. Some alternative theories of gravity, modifications to Einstein's relativity, predict different behaviour in low-density environments like voids than standard gravity does. By studying how matter moves in voids and how structure forms there, cosmologists can test whether Einstein's theory holds up in these extreme low-density conditions or whether modifications are needed. So far, standard general relativity seems to work fine in voids, but the tests are not yet precise enough to rule out all alternative theories. The philosophy of science offers perspectives on what it means to make observations from an unusual location. The principle of mediocrity, or the Copernican principle, suggests we should assume we are typical observers unless evidence proves otherwise. This principle has served science well historically. It led to the rejection of geocentrism, the idea that Earth is the centre of the universe. It supports the cosmological principle, the assumption that the universe is roughly the same everywhere when viewed on large enough scales. But the KBC void seems to violate mediocrity. If our location is a 1 in 1,000 statistical rarity, we are not typical. Does this mean we should abandon the Copernican principle, or should we interpret the principle more carefully? Perhaps it means we should not assume we are typical without checking, but it does not forbid us from being atypical if the evidence says we are. The distinction is subtle but important. Some philosophers argue that observer selection effects might explain why we find ourselves in an unusual location. If conditions in voids are particularly favourable for the development of intelligent life, then most observers in the universe might live in voids despite voids being rare. This would make void observers typical among observers, even though void locations are atypical in space. This anthropic reasoning is controversial. It explains observations by reference to the requirements for observers to exist. Critics argue it is unfalsifiable and unscientific. Proponents counter that in some situations, particularly in cosmology, where we have access to only one universe, anthropic reasoning is unavoidable. The debate continues among physicists and philosophers. Regardless of philosophical stances, the practical question remains how to do good science from an unusual location. The answer is to observe as widely as possible, looking beyond local conditions to see the universe at large. This is what the next generation of surveys aims to do, mapping structure across billions of light years, far beyond the KBC void, to see whether our local observations hold up globally. The ongoing expansion of astronomical datasets is remarkable. Just a few decades ago, catalogues contained thousands of galaxies. Today, they contain billions. Surveys like the Sloan Digital Sky Survey, which began operations in 2000, mapped millions of galaxies across a quarter of the sky. Its successor surveys are going deeper and wider, approaching complete maps of all galaxies visible to a certain magnitude limit across the entire sky. These surveys reveal cosmic structure in ever greater detail. The cosmic web becomes more intricate, with smaller filaments and voids emerging within the larger structures. Each new survey discovers new features, new voids, new superclusters, adding to our understanding of how matter is distributed throughout space. The Euclid Space Telescope, launched in 2023, is designed specifically to map dark matter and dark energy across cosmic history. It will observe billions of galaxies, measuring their shapes distorted by gravitational lensing to map dark matter distribution. It will measure galaxy positions and velocities to trace how structure grew over time. The data from Euclid will transform our understanding of cosmic structure, including voids. The Nancy Grace Roman Space Telescope, scheduled for launch in the late 2020s, will conduct even larger surveys. With a field of view 100 times larger than the Hubble Space Telescope, Roman will image enormous areas of sky quickly. Its infrared observations will penetrate dust and reveal galaxies too faint or distant for ground-based telescopes. Roman surveys will extend deep into the universe, seeing structure as it was when the universe was just a fraction of its current age. Ground-based surveys are also advancing rapidly. The Vera Rubin Observatory, beginning full operations soon, will conduct the legacy survey of space and time, photographing the entire visible sky every few nights for 10 years. This will create a time-lapse movie of the universe, revealing transient phenomena like supernovae and tracking how galaxies move over time. The survey will catalogue tens of billions of objects, an unprecedented dataset for studying cosmic structure. With these enormous datasets, cosmologists will be able to test the void hypothesis conclusively. They will map voids throughout the observable universe, comparing their properties and seeing whether the KBC void is truly unusual or part of a population of similar structures. They will trace how voids evolve over cosmic time, seeing young voids billions of years ago and comparing them to mature voids nearby. They will measure expansion rates and structure growth rates in void versus non-void regions, definitively testing whether voids bias cosmological measurements. The theoretical tools for analysing this data are also advancing. Machine learning algorithms can identify patterns in vast datasets that human astronomers might miss. Neural networks trained on simulated universes can learn to recognise the signatures of different cosmological models in observed galaxy distributions. These AI tools are becoming essential for extracting maximum information from modern astronomical surveys. The combination of vast datasets and powerful analysis tools promises to resolve many of the outstanding questions about voids in the next decade or two. We stand at the threshold of a new era in cosmology, where the amount and quality of data available will transform our understanding. The mysteries that puzzle us today, the questions about voids and their effects and our position within them, may soon have clear answers. Yet even as some questions get answered, new ones will emerge. This is the nature of scientific progress. Each discovery raises new puzzles. Each answer prompts new questions. As we learn more about voids, we will undoubtedly find aspects of their behaviour or properties that do not fit our current theories. These anomalies will drive the next generation of research, leading to deeper understanding. The study of cosmic voids exemplifies how scientific knowledge grows. It begins with unexpected observations, galaxies in the wrong places, densities that do not match predictions. These anomalies get investigated carefully, checked and rechecked to ensure they are real. Once confirmed, they force scientists to question assumptions and revise theories. The process is messy, with false starts and dead ends, debates and controversies. But gradually, through the collective effort of the scientific community, understanding emerges. The void around us is a gift in this sense. It provides a natural laboratory for studying low-density environments and testing cosmological theories. It challenges us with puzzles like the Hubble Tension. It forces us to think carefully about observer bias and cosmic typicality. In doing so, it pushes our science forward, deepening our comprehension of the universe. This is perhaps the deepest lesson the void teaches: that the universe is not only vast in space and time, but also in its variety and complexity. That it contains environments ranging from the ultra-dense cores of galaxy clusters to the near emptiness of cosmic voids. That each environment offers unique insights into physical laws and cosmic evolution. That by studying them all, we build a complete picture of reality. We live in the void, and the void is part of us in the sense that our existence, our observations, our very perspective on the cosmos is shaped by this environment. The light that reaches our telescopes has passed through the void, carrying information about its passage. The galaxies we see move through space, influenced by the void's dynamics. Our measurements of cosmic properties are filtered through the void's effects. To understand the universe, we must understand the void. To understand the void, we must recognize it as our cosmic home. In the grand cosmic story, voids are not merely empty backdrops. They are active participants, shaping structure formation, influencing galaxy evolution, and determining the universe's ultimate fate. They represent the triumph of dark energy over gravity, the regime where the mysterious repulsive force dominates completely. By studying them, we probe the nature of dark energy, perhaps the deepest mystery in all of physics. The future holds promise for resolving these mysteries. With new telescopes, new surveys, new computational power, and new theoretical insights, we are positioned to make dramatic progress in understanding voids and their role in the cosmos. The next few decades will likely see major advances in cosmology, driven partly by improved understanding of large-scale structure, including voids. As we look ahead, we can anticipate discoveries we cannot yet imagine. History shows that new observational capabilities always reveal unexpected phenomena. When the first large galaxy surveys were conducted, no one predicted the cosmic web structure with its filaments and voids. It was a complete surprise. Similarly, future surveys operating at higher sensitivities and across larger volumes will surely discover new features of cosmic structure that challenge current understanding. These discoveries will refine our picture of the universe and our place in it. They may confirm that the KBC void explains the Hubble tension, resolving that crisis, or they may reveal that the tension has a different cause, pointing toward new physics. Either outcome advances our knowledge significantly. They may show that voids like the KBC void are more common than current statistics suggest, relieving concerns about our cosmic typicality. Or they may confirm that our void is exceptionally rare, raising deeper questions about why we find ourselves here. Again, either outcome informs our understanding. They may reveal new properties of dark energy, showing how it behaves in different environments and how it has evolved over cosmic time. They may constrain dark matter properties by mapping its distribution in voids with unprecedented precision. They may test gravity in new regimes, either confirming Einstein's theory or revealing deviations that demand new physics. All of these possibilities are exciting. They represent the frontier of human knowledge, the edge of what we know pushing out into what we do not yet understand. This is why cosmology is such a vibrant field, attracting brilliant minds from around the world. The questions are profound, the challenge is immense, the potential rewards transformative. For those of us who look up at the night sky and wonder about our place in the cosmos, the void offers a humbling perspective. It reminds us that we occupy a small island of matter in an ocean of emptiness, that the universe is far larger and stranger than everyday experience suggests. That reality operates on scales both vastly larger and vastly smaller than human perception, governed by laws that seem alien to our intuition, but can be understood through patient observation and careful reasoning. The void also offers a strangely comforting perspective. Despite its emptiness, Despite the vast distances and the isolation it implies, we are here. Life arose on Earth, intelligence evolved, and now we study the very void that surrounds us. The universe may be mostly empty, but it is not devoid of meaning or purpose in the sense that conscious beings exist within it, seeking to understand it. We are the universe becoming aware of itself, studying its own structure and history and fate. This realization connects the study of cosmic voids to the deepest questions of existence. Why is there something rather than nothing? Why does the universe have the properties it does, allowing for the emergence of complexity and life and mind? What is our relationship to the cosmos that gave birth to us? These questions have been asked throughout human history by philosophers, theologians, and scientists. Modern cosmology cannot answer all of them, especially the most fundamental, why questions that may lie beyond the scope of science. But it can answer many of the how questions. How did the universe begin? How did structure form? How did galaxies and stars and planets arise? How did we come to exist in this particular location, in this particular cosmic epoch? The answers cosmology provides are often surprising and counterintuitive. The Big Bang origin, the inflationary exponential expansion, dark matter and dark energy, the cosmic web with its voids and filaments, all of these were unexpected discoveries that overturned previous assumptions. Yet they are now established facts, supported by overwhelming evidence from multiple independent observations. The void around us is one more surprising fact about the universe, one more piece of the cosmic puzzle falling into place. It may seem strange or unsettling to learn that our location is unusual, that we dwell in a statistical rarity, but strange and unusual does not mean impossible or meaningless. It simply means that the universe is more varied than we might have guessed, and that our particular corner of it has special properties worth understanding. As we conclude this journey through cosmic voids, through the science and philosophy and implications of dwelling in empty space, we return to where we began. You are falling through a hole in space, the KBC void, 2 billion light-years wide. This is your cosmic address, the environment that has shaped your existence in subtle ways, from the apparent expansion rate you would measure if you were an astronomer, to the night sky you see filled with stars from our own galaxy, but remarkably few other galaxies compared to what observers in denser regions would see. This hole in space is not a defect or an absence of something that should be there. It is a natural feature of cosmic structure, arising from the same physical laws that govern everything else in the universe. It is as much a part of the cosmos as the galaxy clusters and superclusters, the stars and planets, the atoms and molecules. To understand the universe completely, we must understand the voids that comprise most of its volume. The scientists who discovered the KBC void did not set out looking for it specifically. They were simply counting galaxies, mapping their positions, trying to understand large-scale structure. The void revealed itself through careful data analysis. This is how science often works. You look closely at nature with open eyes and an open mind, and nature surprises you with discoveries you did not anticipate. The ongoing study of the void continues this tradition. Researchers around the world analyze data from multiple surveys, run sophisticated simulations, develop new theoretical models, all working to understand this vast emptiness that surrounds us and what it means for cosmology. Their work proceeds slowly and methodically, testing hypotheses against data, revising theories when necessary, gradually building consensus. This process may lack the drama of popular science fiction, but it has its own excitement and satisfaction. The excitement of discovery, of finding patterns in data that no one saw before. The satisfaction of solving puzzles, of explaining observations that seemed contradictory. The deep intellectual pleasure of understanding something fundamental about reality. For those who participate in this scientific endeavour, whether as professional researchers or informed enthusiasts following the latest discoveries, the void is endlessly fascinating. It raises questions about gravity and dark energy, about cosmic evolution and structure formation, about observation and epistemology. It connects to the biggest unsolved problems in physics, while also being a concrete, measurable phenomenon, that we can study with existing technology. For those who simply want to understand their place in the cosmos, the void offers perspective. It shows that Earth is not at the center of anything special, yet our location has properties that influence what we observe. It shows that the universe is mostly empty, yet the islands of matter within the emptiness have given rise to complexity and life. It shows that scientific observation from our specific position can still reveal universal truths, as long as we are careful and honest about our observational biases. The void, ultimately, is a window into the nature of the cosmos. Through it, we see the interplay of gravity and dark energy, the growth of structure from tiny primordial fluctuations, the evolution of the universe from smooth uniformity to intricate complexity. We see that emptiness is not passive nothingness, but an active force shaping cosmic destiny. We see that our moment in cosmic history is special. We live in an era when the universe still has rich structure, when voids are features among galaxy networks rather than the entire landscape. Billions of years in the future, when dark energy has had time to dominate completely, the distinction between void and non-void will vanish as everything becomes void. Future observers, if any exist, will see a universe utterly different from ours. We live in the cosmic afternoon, in a sense, when the universe has cooled and calmed from the violence of its birth, but not yet settled into its finally quiet state. We live when stars still shine brightly, when galaxies still cluster together despite cosmic expansion, when the cosmic microwave background is still detectable and the Big Bang's evidence still clear. This is a privileged time for cosmology, when the universe is old enough to have formed complex structures, yet young enough that we can still see its history. And we live in the void, in a statistically unusual location, with all the peculiarities that entails. This is our cosmic context, our place in space and time. Understanding it helps us understand ourselves and our relationship to the larger universe. We are not outside observers looking at the cosmos from some detached vantage point. We are part of the cosmos, embedded within it, our observations inevitably shaped by our location. Yet despite this embeddedness, despite the limits it imposes, we can still learn universal truths. We can still use mathematics and logic to extend our understanding beyond what we directly observe. We can still imagine the view from other locations, from the dense centers of galaxy clusters or the interiors of other voids, and compare those imagined perspectives to our own. This ability to transcend our particular circumstances through reason is perhaps the most remarkable human capability. The study of voids, then, is not just astronomy or physics. It is also an exercise in perspective-taking, in imagining realities beyond immediate experience. It stretches our capacity for abstract thought, challenging us to think clearly about scales vastly larger and timescales vastly longer than our everyday lives. It trains the mind to deal with complexity and uncertainty, with incomplete information and competing hypotheses. These cognitive skills, developed through engagement with difficult scientific problems, have value beyond the specific domain of cosmology. They represent a way of thinking that can be applied to many aspects of life and society. The careful, evidence-based reasoning that cosmologists use, the skepticism combined with openness to new ideas, the willingness to revise beliefs when data demands it, these are universally valuable intellectual habits. In this way, contemplating our position in the cosmic void serves purposes both practical and philosophical. Practically, it improves our understanding of the universe's structure and evolution, refines measurements of cosmological parameters, and tests fundamental theories of physics. Philosophically, it reminds us of our smallness in the cosmic scale, while simultaneously demonstrating the power of human reason to comprehend that scale. We end, then, where we began, but with deeper understanding. You are falling through a hole in space, but now you know what that means. You know that this hole is called the KBC void, discovered in 2013 by careful analysis of galaxy positions. You know it extends roughly 1 billion light-years in all directions from our location. You know that matter within it is 20% less dense than the cosmic average, making it a significant underdensity. You know that this underdensity affects how we measure cosmic expansion, potentially explaining the Hubble tension that has troubled cosmologists. You know that voids form naturally as structure grows through gravitational instability, with matter flowing from underdense regions into overdense ones. You know that dark energy dominates in voids, accelerating their expansion faster than the cosmic average. You know that voids occupy roughly 90% of the universe's volume, making them the dominant feature of large-scale structure, even though galaxies capture our attention. You know that living in a void might be statistically unusual, raising questions about cosmic typicality and observer selection. You know that it might affect our understanding of cosmology in ways we are still working to quantify. You know that future surveys and observations will test whether our location truly biases our measurements, or whether we can trust our current cosmological models. You know that voids are not empty in the absolute sense, but contain sparse distributions of galaxies, dark matter, and dark energy. You know that void environments differ from dense environments in ways that affect galaxy evolution, and possibly the emergence of life. You know that the universe's long-term future is dominated by voids as dark energy drives ever faster expansion, eventually leaving isolated galaxy clusters separated by horizons beyond which they cannot see or communicate. You know all of this because humans looked up at the sky, built telescopes, developed theories, analyzed data, and gradually pieced together the cosmic story. The void was hidden in plain sight all along, waiting to be recognized. Its discovery represents one chapter in the ongoing saga of scientific exploration, the human drive to understand the universe we inhabit. This drive continues. New questions replace old ones. New mysteries emerge even as old ones are solved. The void will keep cosmologists busy for decades to come, providing data to test theories and puzzles to sharpen understanding. Meanwhile, the void itself continues its slow evolution, expanding as dark energy pushes its boundaries outward, emptying as its sparse matter is diluted across ever larger volumes. On human timescales, the void is essentially unchanging. On cosmic timescales, it is dynamic and evolving. This dual perspective, seeing things simultaneously through human and cosmic lenses, is characteristic of astronomy and cosmology. We must bridge between our immediate experience and the vast scales of space and time that the universe operates on. Doing so requires both rigorous mathematics and vivid imagination. The void rewards both. Mathematically, it challenges us to model complex gravitational dynamics in underdense regions. Imaginatively, it invites us to contemplate what it means to live in an ocean of emptiness, to be one of the rare concentrations of matter in a universe that is overwhelmingly vacant. As you rest tonight, as you close your eyes and drift towards sleep, you can carry with you this cosmic perspective. You are in the void. The void is around you, stretching billions of light years in every direction. Yet here you are, alive and conscious, a product of billions of years of cosmic and biological evolution. The atoms in your body were forged in stars, scattered through space by supernovae, gathered into the cloud that formed our solar system, assembled into the Earth, and eventually organized into living beings. You are, quite literally, made of star stuff, as the astronomer Carl Sagan famously said. But more than that, you are void stuff in the sense that you exist within and are shaped by this particular cosmic environment. The void's properties, its underdensity and dynamics, are part of your cosmic heritage, part of the context that makes your existence possible. This is a thought to carry into dreams, a meditation on cosmic interconnectedness. We are not separate from the universe we study, we are expressions of it, local concentrations of complexity in an overwhelmingly simple cosmos, conscious beings in a mostly unconscious realm. The void reminds us of this, puts our existence in perspective, shows us simultaneously how insignificant and how remarkable we are. Insignificant because we are tiny, brief, inhabiting one small planet in one ordinary galaxy, in one void among many. Remarkable because despite that insignificance, we can understand our situation, map the void around us, trace cosmic history back to the Big Bang and forward to the distant future. We can comprehend billions of light years and billions of years despite experiencing only a tiny fraction of space and a brief flicker of time. This is the paradox of cosmic consciousness, of beings evolved to survive on one planet's surface who nonetheless can grasp the universe's vastness. It is humbling and empowering simultaneously, shrinking our egos while expanding our appreciation for what mind and reason can achieve. The void, in its silent emptiness, bears witness to this achievement. It existed long before humanity evolved, long before Earth formed, long before our sun ignited. It will exist long after all of these have passed, expanding ever outward, growing ever emptier, lasting until the universe's final state. Within its vast volume, a brief spark of consciousness has arisen, looked around, and recognized the void for what it is. That recognition, that moment of cosmic self-awareness, is worth celebrating. It represents a triumph of human curiosity and ingenuity, a victory for the scientific method, and a deepening of our collective understanding of reality. The void has been understood, at least partially. Its mysteries are being unraveled. Its effects on our observations are being quantified. Its role in cosmic evolution is being appreciated. This is why we explore, why we build telescopes and train scientists, why we fund research and conduct surveys. To understand, to know, to see clearly what is true about the universe rather than imagining or guessing. The void is now known to science because humans made the effort to know it, invested the resources and intellectual labor required to map cosmic structure across billions of light years. This knowledge is part of humanity's collective inheritance, available to anyone willing to learn it. You now have that knowledge. You understand the void around you. You recognize your cosmic context. You see the universe a bit more clearly than before. This is progress in the deepest sense of the word, advancement toward truth and understanding. As you fall through this hole in space, this 2 billion light-year wide ocean of emptiness, you fall with knowledge, with awareness, with the hard-won comprehension that countless scientists across generations have built. You fall not blindly, but with eyes open, seeing the cosmic web stretched around you, understanding how it formed and how it will evolve. You fall through the void, and you are awake within it, conscious within the cosmos, a small but significant part of the universe's ongoing story. This is your place. This is your time. This is your cosmic home. The void surrounds you. The universe embraces you. And in this vast emptiness, in this infinite space, you exist, you think, you understand. Sleep well, cosmic traveler. Dream of void and stars, of gravity and light, of the infinite expanding universe of which you are an inseparable part. The void awaits tomorrow's questions, tomorrow's observations, tomorrow's discoveries. But for now, rest. Rest in the knowledge that you have glimpsed something vast and true, something fundamental about reality and your place within it. You are falling through a hole in space, and now you understand what that means.